Hello, and welcome to Lesson 5 of CE 3372 Water Systems Design. The topic of today's lesson is storage and storage concepts as it applies to water distribution systems and a little exploration in wastewater and stormwater collection systems. So storage is used in water supply, stormwater management, and wastewater systems for a variety of reasons. There's three primary ones in the water supply side. First is service storage, which is used to produce for flow equalization. Generally, we design things for a steady flow rate, and storage is used to accommodate variable flow rates in a system. That's how it's used in water supply. Flow equalization is also used in wastewater treatment. A secondary reason for the water supply is for emergency storage. That's to supply water during repairs and other system interrupts. And a third reason, not sure I spelled that right, is fire storage, and that's used to provide supply during firefighting activities. And one could logically consider that part of emergency, but fires happen more often than supply emergencies or system emergencies. We might actually get to witness some of that in the upcoming hurricane that's going to hit the eastern coast of the United States in a few days. In those cases, the purpose of emergency storage will be when they lose electricity. At the very least, they can keep the system somewhat pressurized to allow to prevent contamination from getting into the system during restoration of services. Storage is either elevated, which would be above ground, at grade, which is on the ground, or below grade, subsurface vaults, not aquifers. Here's a diagram illustrating the storage compartments. I'm showing fire as blue, flow equalization green, and emergency is red. If you did stack them in a tank this way, it would make sense to me that the fire storage would be the highest part of the tank to guarantee as much pressure as possible. Flow equalization in the middle, and then emergency is reserved at low but adequate pressures to supply the emergency water during a repair. Fire storage, by definition, is storage that's sufficient to allow the system to meet routine use plus substantial fire flow. The desirable volume is based on the expected fire flow rates multiplied by the time required for that fire flow. In some communities, fire flow time is not very much, not because of lack of need, but because lack of physical infrastructure capability. In other communities, less so, and that's generally going to be a size based on the size of the community, the number of customers, how long it's been in service, and similar considerations. But fire storage is certainly an important part of the storage. Flow equalization, or what's called service storage, is sufficient storage to account for peak demands in the system without having to exceed supply capacity. A desirable volume, for lack of any other ways of measuring it, would be about 1 to 2 days of average daily demand. Emergency storage is that which would allow the system to operate without external supply sources for a period of time to allow for repairs or other unusual circumstances. Without emergency storage at all, every single system upset will lead to a boil water order or substantial interruption of service. These kind of interruptions should be rare if the system's well engineered, and having emergency storage again allows those interruptions to be very rare occurrences. A desirable volume is also 1 to 2 days of average daily demand. So how much do we choose? Well, engineers, we want to make it as big as possible so that we can go home and sit on our porch in our rocking chair and drink mint juleps. Economics will say let's make it as small as possible because this stuff doesn't happen very often anyway, and the engineer has to balance the two competing choices in a design. Additionally, we want to consider residence times. For treated water, we want the residence time not to exceed a reasonable amount of time so that the disinfection residual contact time is maintained. For instance, for chlorine chloramine disinfection, a residence time of 6 to 10 days. The water would still be treated upon leaving such a reservoir. As a reasonable rule of thumb, 8 days is probably workable. That's a little bit more than a week. And anything longer than that, you would have to consider that water is raw again, and then it would need another treatment process. For different types of disinfection processes, that disinfection time might be quite short. The one that comes to mind is hydrogen peroxide and ultraviolet visible light disinfection. They don't leave they don't leave any residual. So you couldn't store that water very long and still declare it treated. The hydraulic retention time, you had that in environmental engineering. That's simply the tank volume divided by the flow rate, has units of time, and it tells on average how many days a water molecule coming into that tank will stay there before it leaves again. Surface storage is what we're going to talk about next, and this deals with the purpose of storage reservoirs, the types, and calculating requirements. So we've talked about equalizing or operating storage. It's to equalize pumping rate into reservoirs and provide storage for peak demands. Fire and emergency pressures are also provided by storage tanks, and the three types of tanks are surface, standpipes, and elevated. Surface reservoir is desirable when the natural elevation is sufficient to allow it. It's for relatively inexpensive pump storage operations. That's a desirable side benefit. They're usually covered for protection from contamination, algae growth, and evaporation, and for high school kids peeing in them. And they provide adequate temperature control. Standpipe, you can think of that as a very tall glass, not made out of glass. Think of it as a pipe that's oriented vertical instead of horizontal, where the height is much larger than the diameter. The useful storage is equal to the volume above the elevation needed for the minimum pressure, wherever that is. And then low storage is available for emergencies, because even during emergency, we can use booster pumps if we have to maintain pressure. And they're made out of steel, reinforced concretes, and similar materials. Elevated storage, these are the ones that are hung up in the air. They usually have smaller dollar per volume of useful storage. There's a strong structural component. The foundation design matters. There's wind uplift, earthquake stresses, plus you're holding a lot of water up in the air. The kinds of storage tanks that fall into this category would be hemispherical bottoms, double ellipses, radial cone, Hydra Pillar, and similar things. We're going to look at some pictures shortly. And they can store substantial amounts of water, 3 million gallons, which is a fair amount of water. They also have an added benefit, at least the elevated ones, is you can paint the name of your high school football team on them. So here are a few examples. These are composite elevated tanks, composite referring to the materials. So these are going to be concrete and steel pillars, and the tank itself might be steel or a polymer or a combination of the two. So here we have one that's an ellipse and an ellipse, so there'll be double elliptical. This is a cone with a cylinder part. Here's another cone with a cylinder part. There's probably a curvature on the inside. There's probably walk space inside that, but I wouldn't know without actually going up into it. This one's convenient because it looks like they mounted clocks on it. These ones have small logos. Here's a Hydra Pillar, so that's a trademarked name, so it's can be used for storage in the bottom. There's a pillar in the middle somewhere that actually is the pipe that brings water to and from storage. Presumably you could actually make several pillars. I don't know if that's done, but these could store a substantial amount of water. Here's some other examples of Hydra Pillars. So here's one with a clock on the side, almost looks like a teacup, and then this looks like a space station. So if you saw Men in Black, these are also used for defending the planet against aliens. Just kidding. Interestingly, these photos don't have high school football team names on them. Go figure. Here are some water spheroids of different, they all pretty much have the same shape. This one's got a big peach on it, so that must be somewhere in Georgia, I bet. Here's one at a Cabela's. And then here's a ground level standpipe. So this is a fairly tall tank. And these are, I would call these surface reservoirs. I guess they meet the, they sort of meet standpipe, but you've seen these all over the countryside. Here's some other surface reservoirs. Reservoir, reservoir, and this is a standpipe. The difference between the surface reservoir and standpipe is in a surface reservoir the diameter is bigger than the height. Standpipe, the height is bigger than the diameter. In standpipes, there's some attention made to mixing to be sure that the water coming in is mixed, so you don't get nasty, yucky water at the bottom coming out and making everybody sickly. And then here's some composite elevated tanks, and as an example of the kinds of capacities and heads, anywhere from 1 to 3 million gallons. The pedestal diameter from 36 to 60 feet. The head range 40 to 45 feet of working head, and then the tank diameter is 70 to 120 feet in diameter. So a lot of the storage is in the diameter part, and the head range is fairly narrow, and that sort of makes sense because we're having to hold all that water in the air, and we're going to be structurally limited at some point. And getting it too high, the wind loads are going to be oppressive. So to determine the size of the tanks, we would follow the following guidelines. We'd figure out the hourly demand for a design day, calculate the cumulative draft, so that's the amount of water that accumulates over that design day. Think of the gallons per minute for a particular hour integrated out for the whole day. We'd plot the cumulative draft versus time for a 24-hour period. We'd draw a diagonal line that represents constant rate pumping, and then we read the required storage as the sum of the two maximum deviations. So here is the diagram. So the cumulative draft is this line right here that the cursor is following. We'll actually do it in cursor red baron. Red it is. So here's the cumulative draft. So that's based on the design flows, the estimated demands for a particular hour of the day. Forgot that that's not actually drawing a line. So this line that's supposed to be following the dashed line, that would be the cumulative supply, if you will, of a pump operating at some constant speed. So it looks like 1 hour, so it looks like it's doing 0.25 million gallons per hour of pumping, and you run that for 24 hours and you get to the same endpoint. If we look at these two plots, there's a location here where the two lines are farthest apart on this side, and the two lines are farthest apart on this side. In the case of this point 1, if we subtracted demand from supply, we get a positive number. And at point 2, if we subtracted demand from supply, we'd get a negative number. So we take the biggest negative and the biggest positive, absolute value of them, add them together, and that's the required storage. We can also consider different pumping times. For example, if we're only going to pump for 12 hours, our pumping rate is going to be quite a bit different, and we need to consider, again, the biggest deviations between the supply and the demand lines. Here's an example problem. Suppose that we're given the average hourly demands in the table below. So here's time, here's elapsed time, here's time clock time, and the hourly demand, however it's obtained, maybe from historical records or a nearby community, and we find the gallons per minute for a particular 24-hour period. We accumulate it, so here's this 2370 gallons per minute for 60 minutes is 142,000 gallons. 2252 for 60 minutes is 142,000 plus whatever the 60 minutes times 2252, and it occurs in this cell. And then these are just accumulated, and that's what produced this curved line with the blue dots in it. And then we're going to go ahead and specify a pump rate so that it starts at 0 at time 0 and it ends at the same cumulative value, 7.359 million gallons at the end of 24 hours. So we take the 7.359 million, divide by 24 to get gallons per hour, divide by 60 to get gallons per minute. It turns out a uniform flow rate of 5,110 gallons per minute would produce this black line. Essentially, the slope of that line is 5,110 gallons per minute. Then we'll go ahead and accumulate the uniform supply. So that's this column. Same arithmetic as for this column, but working on different flow rates. And then we take the difference between the two. So we take supply minus the demand, and we accumulate it in this column. And then we look for the largest positive, in this case 981,000, and the largest negative, minus 353, and the sum of those two values. So 981 plus 353,000 is 1.3 million gallons, and that is the desirable equalization or service storage for these conditions. If we were to play the same game but over a different pumping period, you see the pumping rate changes. So much steeper curve, and it turns out the maximum and min in this particular diagram occur at the endpoints, and that may or may not always be true. It depends on where the starting and stopping times of the pumpage occur. And then here's one starting at time 0 and ending at noon, and the only deviation in this case is the last one, the 4.6 million gallons per day. So let's look at those three cases: 4.6 million gallons, 2.7 million gallons, or 1.3 million gallons. So if you can pump for 24 hours, you can pump at a much smaller flow rate and you have smaller storage requirements. If, however, your pumping is limited to a 12-hour interval, it depends on when you start and stop those pumping. The engineer needs to decide which demand to use, whether you want to use daily or peak, even if you have either of those two. Daily is probably adequate. Peak, if you have access to it, might be pretty smart. The volumes are added to that needed to emergency and fire flow, and that determines the tank volume required. Then once you know the volume, then the tank type can be selected: elevated, at grade, buried. That determines the shape, elevation, diameter, minimum levels, maximum level. And elevated tanks have substantial structural considerations. This stuff is not ancient history. These are still done today. Here's an example of a January 21st, 2014, that's only 4 years ago, of a desire to modify a storage tank here in this image in Far, Texas. And the 1 million gallon elevated tank is being added to maintain, in this case, service pressures in their community. Stormwater storage, similar idea. It's used to mitigate peak flows. It provides some water quality benefit and can be used to develop a water resource. In stormwater, we aren't always constrained. We're not about to pump water in the air, but we tend to store it underground as an option. So these underground storage tanks are more than just a hole in the ground. There needs to be structure to support surface loads, and there needs to be a way to completely drain it. In the picture on the left, it's done by pumping. In the picture on the right, this is underneath a cistern ring. This is in San Francisco, California, and this particular location isn't far from where I grew up. There's quite a bit of vertical relief before it gets down to the beach, so there's no really need to pump it. There's just an underground pipe. Let's look at storage and computer models briefly, because this is going to play an important role shortly. So storage elements in computer programs are tanks or reservoirs. In the case of EPANet, or they're called storage junctions or storage elements in SWIM. They both have similar minimal data requirements, and those include where the bottom of the tank is, or the bottom of the node that it's connected to, whatever the minimum pool elevation, usually measured above the invert elevation, the beginning pool elevation, also above the invert elevation, the maximum pool elevation, also above the invert elevation, and then something that has tank dimensions or depth storage curve. So here's a diagram depicting some arbitrary tank connected into a hydraulic network. In this particular one, this tank is connected to node 2. There's a portion of the pipeline that's 180 feet long horizontal and then 120 feet long vertical. The entire pipe would be entered into the program as 300 feet because the horizontal vertical, unless we're going to introduce a node right there, we don't have any way to distinguish that. We set the bottom elevation of the tank at 180 feet. The minimum level is equivalent to elevation 300 and the maximum level is equivalent to elevation 315, but we would actually probably supply the min level is 120 feet of depth and the max level is 135 feet of depth, and you add that to the 180 to get these required minimum maximum levels, and then we'd have to supply a starting condition. The tank dimensions would have to be something sensible. You had that table earlier to give you some rough ideas. An alternative is we can use a volume versus depth table to convey tank storage capabilities. It's quite similar to reservoir routing in hydrology. And so when we get to that in the course, we will discuss it.